In this recording, we're going to talk about water, because water is the foundation for all biochemistry. So all the biochemistry, all the chemistry involved with life, that as we know it, happens in water. So the background for everything that we see is this water-based environment. Now, water is kind of a weird substance, and there are 6 characteristics of water that are going to affect life that we're going to know. So you're going to see this slide again and again, because repeat is a good way to learn. We're going to know that we're going to learn about water as a polar molecule. We're going to talk about how water forms hydrogen bonds, that water is cohesive, water is a good temperature buffer, it's less dense as a solid, and it's an excellent solvent. So let's talk about the polarity of water. So if something is polar, means it has ends, right? So think about the polar ice caps that are on the ends of the planet, the North and South Pole. Well, water is also polar. It has a partial charge on one end and a partial charge on the other end, and those charges are opposite. One end is partially negative, and one end is partially positive. And that's what that kind of funny curly Q Greek lowercase delta represents in this picture. Now, we know water is a covalent molecule, so the hydrogens are covalently bonded to the oxygen. So they're sharing electrons. And what this brings up is a topic that we talked about briefly during our chemistry lecture, and that is electronegativity. So again, electronegativity is a tendency for an atom in a bond to draw the electrons in that bond to itself. Right? And oxygen is very electronegative. And so what we're going to see, and that's what these arrows represent here, is that the electrons that oxygen is sharing it's not sharing them fairly. So they're sharing, yes, but they're spending more time with oxygen than they are with hydrogen. And we know that because electrons are negatively charged, now those negative electrons, if they're spending more time with hydrogen, are going to impart a partial negative charge to that end of the molecule. This is not an ionic molecule. These are not ionic bonds. But because of the electronegativity of oxygen, the electrons, the negative charge, is going to spend more time on that side of the molecule. And hence, the electrons around the H's, they spend less time there, and the protons in the hydrogen atoms are less shielded. And so a little bit of that positive charge kind of leaks out, and you get a partial positive charge on that molecule. You can think of a water molecule as kind of like a tiny magnet. One end has a little bit of attraction, the other end has the opposite attraction, right? So we call this a polar molecule. One end is partially positive, one end is partially negative. So what we're going to see is that this first characteristic of water, water is polar, is going to be kind of the foundation for most of the other characteristics. So we're going to build from there. Now, because of this polarity, because of this partial charge, we can form what are called hydrogen bonds. And these are special kinds of bonds that are not very strong. They're quite weak, in fact, and they're transient bonds. And this forms, as you might expect, where the positive end of hydrogen, the positive end of the hydrogen end of the molecule, wants to be with the negative end, right? Because remember, positive and negative attract. This is electrostatic forces. And so water molecules, as they move past each other, are going to rotate and be in a way to be like, hey, here's my negative end. I want to get it close to your positive end for as long as we can. And that attraction, for just a moment, it's called a hydrogen bond. All right? Those are going to be essential to how this works. Now, other molecules that are polar can also form hydrogen bonds. So anytime you have a strongly electronegative atom in a molecule as simple as these, this is ammonia with water, you're going to form that polarity. And that polarity then can work to form hydrogen bonds between different molecules. So water is forming hydrogen bonds with other water molecules all the time. Okay? This is actually going to lead to the cohesiveness of water. So water is cohesive. What does cohesive mean? Cohesive means you stick to yourself very well, right? And so obviously, if every water molecule has a little bit of positive and a little bit of negative, then the positive ends are going to try to stick to the negative ends of other water molecules, and the negative ends are going to stick to the positive ends of other water molecules. It holds itself together. And this characteristic is actually very important for how water moves through plants. And so water is drawn up from the roots to the leaves because we're pulling on the water molecules in the leaves, and because water is so cohesive, it actually draws the whole column of water up through what's called the xylem through the plant. And we'll talk about this more later. This also leads to surface tension, right? Because the water molecules are hanging together, they actually can support, in this case, a water walker, like a water skimmer, an insect. Okay, so that's a very real characteristic of water, that it is cohesive. So water is polar. Because it's polar, it forms these hydrogen bonds. Because of the hydrogen bonds, it's quite cohesive. Also because of those hydrogen bonds, water is a very good temperature buffer. It can take a lot of energy to warm up water, and that energy that you can actually store in water, you can remove a lot of that energy before the temperature of the water drops. This actually acts as a global temperature regulator. Right? So this is why when they talk about the average temperature of the ocean rising even a few tenths of a degree, it's a tremendous amount of energy that you put in the ocean to do that. And this is what are good indicators of the fact that we do experience climate change. In general, though, the fact that we have so much water covering the surface of the planet actually helps to regulate the overall temperature of the globe such that it is habitable for life as we know it. So water is polar, forms hydrogen bonds, is cohesive, acts as a good temperature buffer. Now, the other thing that's weird about water is that the solid form of water is less dense than the liquid form. In general, as things go from gas to liquid to solid, they get more and more dense. And so you can compare here water, liquid water, in it is floating solid ice, the solid form of water. Next to it is benzene. You have a liquid benzene, it's a clear organic solvent, but as it solidifies, it actually gets denser and sinks, and that's the case for most things. Think about metal. As you heat it up, it expands. Things expand as they get hotter as opposed to when they get colder. But water is weird that way. Why? Because of hydrogen bonds. So if we think about liquid water, those hydrogen bonds are moving past each other. The water is in motion, right? Because the energy in that collection of molecules is relatively high. So that energy is kinetic. They're moving around. That's what we think about as temperature, the average amount of energy in that system. Now, as we cool down the system, though, in, for instance, a piece of ice, what's going to happen is those molecules are going to move past each other much, much less quickly. And because of that, then, you allow that positive and negative to kind of latch onto each other. And every positive really wants a negative, and every negative really wants a positive. When you're in liquid water, they're moving so fast past each other that you're kind of always satisfying that. But as I slow the molecules down, they have to orient themselves in a crystal that allows every negative to have a positive and every positive to have a negative. This is the ice crystal, and that actually forces the molecules further apart from each other, becoming less dense. So ice then actually expands as it gets colder and floats. And that's really important, because if it didn't float, we would have ice sinking to the bottom of the oceans and lakes, and then it would repeatedly freeze every season as we layered up ice more and more and more at the bottom until we would have a solid ice pack. So you can see here, using a black background to really show you the difference, you can see gaseous water in the form of steam, water vapor, a lot of black there, liquid water, and then on the far left you can see ice. And in fact, there's more of that black background coming through in the crystal form of ice on the left than in the middle for liquid water. So, water is polar, forms hydrogen bonds, it's cohesive, it's a good temperature buffer, and in a weird way, the solid is less dense than the liquid. But water is also a very, very good solvent. And this goes back to its polarity. So if we think about that ionic bonds that we studied in salt, right? You have positively charged sodium ions and negatively charged chloride ions. And because positive and negative attract, these click together like a little magnet, right? Electrostatic forces. Now, if you put that salt into water, as we all know, it dissolves, disappears, quote unquote. Now, it hasn't gone away. We've just broken it down into its individual ions, and those are equally dispersed in the water. Well, why does it dissolve, right? So this idea of dissolution, of things going into solution, is also important to understand. So if we think about a solution, it's a homogeneous mixture of two substances on a molecular level. It's an even mixture of two substances on a molecular level. And so what you call the solvent is, in this case, the liquid, and the solute is what is dissolved into the solvent. So a solution, you have the solvent, what is dissolved into the water. And so water is very good at bringing things into solution because it has positive and negative charge. And so it wants to interact with things that have either partial or total charges, full charge. So the nice thing is, if it finds a positive ion, like sodium, it can turn and face all of its negative charge towards it and surround it and say, oh, you are satisfied because we're giving you plenty of negative charge, and bring you into solution. If it encounters a negatively charged ion like chloride, it can turn its positive side towards it and do the same thing, drawing into solution, satisfying that negative's need for positive by providing it. But water can provide both. So water gives you whatever you need. You need positive, it can give it to you. You need negative, it can give it to you. So this works with relatively large molecules too, like proteins. So we'll talk about proteins later, but proteins are going to be very, very important in biochemistry, regulating your cellular biology. And these need to be in that aqueous solution, that aqueous soup that is the milieu of life. All right? So again, water is polar. Water forms hydrogen bonds. It is cohesive. It's a very good temperature buffer. It is less dense as a solid, and it is a very good solvent. Now, we're almost done with this particular recording, but we want to address one more issue, and that is pH. Because water is the basis of life, water also has this interesting characteristic of having a pH rating, a level of acidity. So you might ask, what is pH? That is just that. It's a scale upon which we can rate the acidity, how acid-like the solution is. And it all comes down to two ions, the hydrogen ion and the hydroxide ion. And as you would see, H and OH together make H2O. And that is the source of these ions. The water actually goes through what's called autoionization. It breaks down and contributes these to solution. As long as they're in very, very small amounts and in equal amounts, you have neutral water. Right? So hydrogen ions, if you look at the hydrogen atom, are also known as protons. Because if you remove the electron to make it positive, all that's left is a naked proton. I point this out because oftentimes I'll just refer to the hydrogen ions as protons, and I want you to know where that's coming from. So again, pH technically is the negative log of the hydrogen ion concentration in solution. So what we have then, because of this weird math twist, the more acidic a solution is, the lower the pH. Right? Now, because it's a logarithmic scale, it's also a 10 times kind of thing. So what we see then is that every step of the pH scale is 10 times more acidic than the previous step. All right? So what we're going to see is that if I have a pH of 5, it's a little bit acidic. pH 4 is 10 times more acidic than pH 5. All right? Now, again, I want you to remember the lower the number, the more acidic. So when we look at this pH scale, you can see pure water is neutral, where the hydrogen ion concentration and the hydroxide ion concentration are equal at 7. Pure water. If we go slightly alkaline, we get to human blood, and more alkaline means I have more and more hydroxide ions. This can be very caustic. Right? So if you get up to oven cleaner, it's very, very high pH. Very, very low pH, now we're down to 1s and 2s. You're talking about battery acid, lemon juice, stomach acid. And so basically, the further away you get from 7 in either direction, the more caustic a solution is. But the more acidic it is, the lower the pH, the more alkaline or basic it is, the higher the pH. All right?